Welcome to the Week 7 lecture for microprocessors and robotics. This week we're going to cover the basics of C programming, so we'll learn about half a dozen basic commands to get you started programming in C language. To go along with that, we'll take a look at the architecture of an Arduino Uno and how that works in conjunction with our C programming commands. And then we'll pull this all together when we review Lab 4. I'll go over that, of course, as usual. And then in a separate video, I will have a setup for your Arduino board. There's not a lot of setup involved, so that should be pretty simple for you to get going. As a quick refresher on our programming languages, or some of the programming languages that are most common, the last couple of labs and weeks we've been focused on assembly language, which you'll notice is second from the bottom. This is a very basic language, so it's not very complex. It's only a step above machine language. So now we're going to take it a step further, and we're going to spend approximately the next 5 weeks looking at our C programming language. And I think you'll find that this language is a lot more flexible, it's easier to use, and it makes a little bit more sense, right? So if you'll recall kind of some of the commands when we talked about it in the previous weeks, assembly language gives you some clues into what the commands are doing by their names, but C language does that even more so. So we kind of not struggled, but we made it through assembly language. So now there should be a light at the end of the tunnel. You should kind of have the basics of programming down a little bit. And so this should make it much easier to learn the C commands and to be able to build programs with those. Here is what's called a pin map of our Uno board. And I'm just going to outline a couple of important pieces of architecture on this board. The first are our pins. So it's very important to know what I'm talking about when I refer to the pins. Let me grab a better color here. So you'll see we have one on the left and we have one on the right. And the pins are all numbered. You can see the ones on the left, there's one's called reset, 3.3V, 5V, G and D for ground. We have ones towards the bottom that start with an A, and on the right side we have our numbered pins. And then we have some other things on the board that I want to draw attention to. So before we get into pins, take a look at this light over here on the board. I've highlighted it in orange. That may be kind of hard to see. There's a lot of colors on this map, and so when I'm going through with my pointer, it's difficult to get a color that will show up against everything else. Let's see. I'll circle it in white as well. Okay, so this is a light on our board. It's an integrated LED is what it's called, and it's tied to pin 13. So if we reference pin 13 in our code, this LED on the board will also take the same action. So if we tell whatever's connected to pin 13 to blink, the integrated LED will blink too. And so we'll be using this in the first part of our lab. And I like to use the integrated LED because there's two components and two places that an error can occur when you're building a circuit or when you're constructing a program. The first is in the actual construction. So if you have something connected wrong or a wire connected incorrectly, your program and your circuit will not function as expected. The second place for error is, of course, your program. And so by programming with the integrated LED, that removes the construction part where there's room for error. So the only error is in your code, essentially, when you're using the integrated LED. So in the first part of our lab, we will be starting with that. You'll also notice up here at the top, there's this large metal box. This is simply where you plug in your cable and connect it to your computer for power. You can connect this to a 9-volt battery by other means, but typically it's easiest to just plug into a computer. You would connect it to a battery if you were doing essentially a wireless operation. Maybe you were using one of these in a robot or in some sort of machine that was moving around, or some sort of construction that was moving and you didn't want to be connected to a laptop, then you wouldn't have to use this and plug it in, but otherwise that's what I would recommend. It's just plugging that right into the laptop. Other things to notice on this board is the integrated push button. So just like we have an integrated LED, we also have an integrated push button that we can use. And we can also connect external push buttons. Now let's go through our pins. So you might notice along the bottom of the screen, we have some different things mapped out here. This is kind of our key at the bottom, and this just tells us the capabilities of each pin. So every pin, every place that you can poke a little wire or component into, cannot perform every function, and that's very important to remember and to refer back to your pin map when you are constructing your circuit to make sure you're using the appropriate pin. Some important pins to know. We'll start on the top left. The 3.3 volts and 5 volts, this is where we would input power to our circuit if we were connecting to a battery and not to our computers. We won't be doing that in this course unless you choose to do so in your project. And so by my direction at least, you will not be using those. We also have a couple of ground pins, and so we have 2 on the left and 1 on the right. So it's always important to ground your circuit, and when I get into the schematics, I'll explain more about what that means. But we have multiple pins to ground to, so you have some options there. And V-in is just another pin that we use when we're using an external voltage. Okay, now on to the very important items to pay attention to, your digital pins and analog pins. So we'll get into it more next week, but digital pins output either a high or a low signal. Analog pins can output a signal that's somewhere between high and low. So if you think of high as being 1 and low as being 0, digital pins are capable of outputting those. And then only certain pins are configured as analog pins that can output values in between those. So that might be a 0.25, 0.5, 0.75, essentially something to that effect. And so next week we'll learn about analog pins and how we can use those to fade LEDs and things like that. But this week we're focused on digital pins. And so you can see through all the blue, we have many, many digital pins. And this just clarifies too, as well, these little numbers in these blue ovals, what the pin number is. So you should be able to easily see the pin number on the board, but then these numbers provide you some alternates as well. So you'll notice on the left, the board says A0 through A5. If you want, you could also refer to these as pins 14 through 19 if you're just using them for digital purposes. That makes it a little bit easier. And then, of course, it says here on the board analog pin, and we see by our green ovals that this set of 6 pins over here are the pins that we have to use for analog functions. So not all pins are configured for analog outputs, just these 6 on the left. And I think your board does a pretty good job of reminding you of what's analog. We label them analog pin on the board, or we don't label them. They come labeled as analog pins. They have an A in front to remind us that it's an analog. Up here in the power section, it's grouped together as power. And then your digital pins, everything on the right side is all digital, and so that's labeled accordingly. Some of these other things we won't get into too much in depth, the AVR pins, SPI pins, I2C pins, those aren't relevant to this course. Those are a little bit required for more in-depth understanding and programming of microcontrollers. SPI and I2C are communication types, so you may eventually get into those, but as I mentioned, we won't be using those in this course. However, two more pins that may be important to you as we go on, depending on your project and what you do, are the serial pins. So we'll talk about serial communication, and that can only be done on these 2 pins right here. the bottom two right pins. You'll see they have the little orange ovals near them. And so that's very important to remember. So I'll get rid of all of this. So you can always look up a pin map of the Arduino Uno. You can reference this photo right here. Or save it for later. But if you're unsure of which pin to use by just looking at your board, you can always refer to this pin map. When it comes to C programming, the first thing we're going to look at is the structure of our program, or how we would set up our program. So if we think back to assembly, we always started our programs with underscore main and a colon, right? And we always end with NOP. And anything within that is our program that runs. And so we have a similar setup. It has a couple more rules, a little bit more structure to it when we're using C. And so we'll take a look at that, kind of the base structure that we're using. So the first thing that you do whenever you're writing a program is declare any variables. You don't have to put anything before them, they just go in lines to the top. So if you'll see this little example, I have in set. We'll review each command and what all those mean after we take a look at the setup and the architecture of your program. The first thing you're going to do is declare your variables. So that's this first line right here. And so I'm simply saying that pin number 14, I'm just going to call it LED pin in the rest of the program. And so you can see I'm kind of assigning a label to that pin. So that's my variable. So the first thing I'm going to do is lay out all my variables in the program and define them like so. Then the next thing we're going to do is use the setup command. And so this is important if we're declaring any pin modes, if we need to set any pin modes to input or output, if we need to bring in any libraries. And so the void setup part of the code is something that will only run once. So your program, it'll start, it'll recognize all of your variables that you've declared, it will run through the setup, and then it's done. It won't refer back to those again. So it's only going through those once, and then it will get into your program loop. So it looks like this down below here. I have kind of the setup. So void setup always starts by declaring your void setup like this. And the case of your letters doesn't matter. So they can be capital or lowercase letters. You'll notice it doesn't really have an effect. In my example, I've got all lowercase. And so after you write void setup, two separate words, you will put in two parentheses right next to each other, open and close. So those come immediately following a void setup. And then it's good practice to do this on separate lines, but after that you'll want to put a curly bracket. So we have our first curly bracket after void setup, and this is where our program goes. We start writing after this first curly bracket. When we're done with our setup, we've declared everything that needs to happen in the beginning, all of our pin modes, any libraries that we need to reference. Once we've defined everything, we will close that with another curly bracket. So this is generally the setup. It's good practice to set this up every time that you start a new program. That way you have it and you kind of know where to fill in your program. You're almost creating fill in the blanks for yourself. So if we look over here at this example on the right, you'll see I have void setup written all in lowercase, and then I have the two closed regular parentheses following it. And this time I kept my curly bracket on the same line, but you have your first curly bracket open, and then I have my setup code in between here. So I only have one line of setup code in this example. I'm just declaring this pin to be an output. I only need to do that once in the program, and it's going to run through this essentially when it starts up. So I'm going to put that in my setup, and then once I am done with all my setup code, I'm going to close that with another curly bracket. So then we'll take a look at what comes after our setup. After we define our variables in the void setup, the next thing to do is going to be to create our void loop. So the void loop is where the main part of our program goes. This is the equivalent of the underscore main colon in assembly programming. So when we're programming in C, we use void loop. And so we set it up like this. We start out with the words void loop, and then we have two closed parentheses, open parentheses, closed parentheses after that, no matter what. And then we have our first curly brace, and then after that will be the main portion of your code down here. And then when you complete your code, at the end of everything, instead of doing an NOP command like we did in assembly, all you have to do is end it with another a closed curly brace. And so the void loop, the name kind of indicates what it's doing here. Instead of just going through the program one time like we did in assembly, when you're setting this up in C and especially in Energia, it's going to be looping through the program. So if you have a pin output connected to an LED and you're having it blink, it's going to keep blinking on and off until you end the program or tell it otherwise. And so it is looping back to the beginning every time. So that's why it's important to declare certain things in the beginning, or declare our variables and start our setup. And just note that anything that happens in the loop is going to be performed repeatedly unless you tell it otherwise. So to emphasize that, I have a little example program drop down in here. So you can see this first line, we're declaring our variable, right? We always do that at the beginning of our program. We're declaring our pin 14 to be an LED pin, and then we're getting into our void setup. So we have a void setup, open and close parenthesis, first curly brace. We have our first line of setup. We're setting a pin as an output. Another curly brace to close that, and then so after we've set this as an output, because we only need to do it one time, so that's why it's in the setup. If it was in the loop, we would keep setting this as an output, which is unnecessary. And it could slow your program down too eventually if you add in too many things that you don't need to repeat. If it's needlessly repeating them, then that's wasted time cycling through those lines. So after our void setup, we have our void loop, open and closed parentheses, and then our first curly brace. And then we start with our first line of code. And you can't see the second curly brace because in the snippet there's more code below here, but when we would get to the end, we would end that with a closed curly brace or bracket. And so it's important to note too, in assembly, indenting was really important, right? When we were working with labels, they were all the way to the left. Everything else, for the most part, was indented over to the right. When we're programming in C, we don't have to be as mindful of that. So you can see on this last line here, void loop, I actually have the first line of my program right after that. Ideally, this would be on a separate line. It's good to keep things nice and neat. Kind of like how in void setup, I have that on its own line, and then the next line of code is a separate command. But so you can do that. That's the best way to do that, is to separate things by line, but you can also have them next to each other. So just a little note there, indenting is not necessary. So that is how we set up our void loop. And just to reiterate, everything in your code that is not just a setup variable being declared one time. So the main portion of your code will go in this void loop between these two curly braces. The last piece of our programming basics is the comments. And so before in assembly, we noted a comment with a semicolon, and they're a bit different in C programming. So before it was a semicolon in assembly, when we're doing C programming in Energia, our comments are actually going to be noted by 2 backslashes. So anything after that is going to be a comment, but the microcontroller does not read. So you can see in my example program, I have these backslashes noting the comments. And you might also notice, you might say, well, there are semicolons there. The semicolons are not what is annotating the comment. The semicolon is actually part of the line before that, kind of signaling the end of that line or command. And so in most cases, you'll need both. You need a semicolon at the end of every line. It's kind of part of the command most of the time. But then you'll also want to put in these 2 backslashes in Energia anytime that you're entering a comment. Here's an example of what I call a shell program. This is where we're stringing all of our basic setup pieces together as kind of a template for ourselves. And so you see at the top, there's no braces or brackets or anything to declare variables, so I've just put in a note here. Any declared variables go at the very top, Nothing has to go before or after them, just in standard fashion, or as a standard command, you would just write it like that. So any declared variables go at the top, and then we would put void setup to parentheses, open curly brace, any setup code here that you're only going to run one time, so you can't loop back to this. Anything that you're declaring, we would put in our setup, close with a curly brace, and then we would start our void loop, or the main part of our program. So like I said, the loop is not continuous, but it does have the ability to return to places within the loop if you program it that way. So then we have our void loop written here. We have our two parentheses, first open curly brace. You'll notice we've got some comments here that are going on. Those are very important. Anything that's part of the main code goes within the loop, and then we close it with another curly brace. And so it's a good idea to copy and paste this into any new code that you have if it doesn't already pop up, just to kind of remind yourself of what needs to go where, and what you need to fill in as we go. So this is essentially our shell program. This applies to anything, any C program that we would be writing in Energia. Since we've looked at how to set up a program and get started, now we're going to jump into some of the basic functions, the things that we can put into our programs. And so we're going to look at several variables that we can declare and different commands that we can use when we're programming with C language. The first command that we're going to look at is the int command, and int stands for integer. So what this does is it's declaring a variable, usually a pin, and it is assigning a label. And so the syntax that this uses when we're setting up this code, we always follow a set format. Just like in assembly, right? We would usually have the mnemonic, a source, and a destination, or something like that as our base setup. And so for the integer command, we have int to start with, and then we would have any name that we would want to assign. So when I say label, that label can be anything that you want, as long as it doesn't look like another command. Then we have the equals, we need this, and then we have a number here and a semicolon following. So this number can be a pin number, it can just be an integer, but typically this is a pin number. And so we see that defined down here in the inputs. So in the syntax up above, name is just referring to whatever label you want to call something in your program, and then the number is typically a pin number. So we can see this in our example code. We have our command declared, int, and our label is going to be LED pin. And we're going to use that to refer to pin 13 in our program. And so sometimes it's easier to declare variables and give them labels. It makes them easier to remember. It makes them easier to refer to in your code. It makes it easier to understand the code. And if somebody else is using your code, it makes it easy for them to understand. So instead of referring to turn on pin 13, turn off pin 13, calling it LED pin and giving it that label, you're reminding yourself that that pin is tied to an LED. Another bonus of declaring all your variables up front, even if you think you can remember them or nobody else is going to work on your code, if pin 13 stopped working and you had to switch to another pin, if you just use pin 13 in your coding, you would have to go through your code and change everything that was pin 13 to your new pin number. If you declare your variable in the beginning, you're just referring to this as LED pin. So LED pin can be whatever you set it to up here. So if you need to change this to pin number 2, your whole program is not changed. You only have to change the pin number in one spot, and then when the rest of your program refers to LED pin, it will already be declared as pin 2. So it's really important to declare things early on and give them labels and declare them. In this case, this is an integer. So this is essentially a number that we're assigning a label. And there's other things that we can assign labels to that we'll take a look at. In addition to integers, we can also assign labels to what we call a character. So much like the alphabet is full of characters, right? We can declare characters with the CHAR command. And so how we do that, looking down at the syntax, we would write our CHR, whatever label or name that we wanted. Last time I called it name, this time we're just calling it a label. Setting it to equal whatever value is in these single quotations. And so looking at our inputs down here, we see, again, the label is just whatever you want to call the character, and the value can be any character you want. So over in our example, when we're using characters, typically we do a single character, or it can be a single number. So we usually try to declare numbers using the integer command, but you can also use the character command. And so you see in both cases, the label here is MYCHAR. That's what we're referring to these as. So we're using the command, we're giving it a label, we're setting it to equal, and then we're putting a character value in here. So this is it. If it's going to be a letter, it needs to be within these single quotations, and then every line here needs to be ended with a semicolon. So this is how we would set up a character value. So what do we do if we need to declare something that's not a number and it's more than a single character? This could be a word, or this could be several words put together. We could declare that with a string, or what's called a string. And so the function of this, again, is just to set any portion of text that's greater than a single character. And so the way we write that is by using the command string. Like I said, you'll notice C is a little bit easier to use and remember the commands for. So we just use string to declare that we're declaring a string. And then we have our label here, which is, again, anything that we want. And then we have our equal sign, and then our text goes in between these double quotation marks. We always close with a semicolon. So this text section can be any text, any word, any string of words that you would like to be labeled. So over here in our example, we see in blue is our command, our string command, and we are calling it string1. And it's going to equal, and you'll see we have it in these double quotations, the phrase hello string, and we end with a semicolon. So anywhere later on in our code where we call out string1, we use this notation here. It is going to recall that this is equal to hello string. So if we asked our microcontroller to print the phrase attached to string1, it would go in and print whatever this was set to. So right now it would print hello string. And again, the advantage to declaring everything in the beginning is that if you need to go back and change something, it is a lot easier to do so. So if you had, for instance, anytime somebody pressed a button an even number of times, you would want the microcontroller to print the word even number of presses. Instead of typing even number of presses everywhere in your code, you could just call it EP. That could be your label. So one, that makes writing your code a lot shorter and easier. Kind of write EP over here. So instead of writing out that super long string every time, you only have to write it once and refer to it as EP later on. If you change your mind and you want to have it say there was an even number of button presses, kind of change up the wording a little bit. Instead of doing that for every occurrence in the code, you only have to do that once at the beginning when you're declaring your variables. So you only have to change that in one spot. And then in every other place, you're just referencing this as EP. So whatever EP equals at the top, that's what it will equal for the rest of the code. So that's the advantage of declaring all of your variables in the beginning of your code. It makes the code easier to write. It's easier to change your variables, and so we just have to keep in mind when we're declaring things what the best command is to use. So if it's a number, integer is a really great way to declare that, especially if you're working with different pins on the board. If it's a single character or single number, we can use the character function. Or if it's a word or a phrase or anything like that, we can use the string function to declare that. This also works backwards a little bit, so you can use string to declare a single character if you really wanted to, although it would be a waste. You can use string to declare an integer if you wanted to, although it would be a waste. Typically, you pick the simplest way to declare something. You declare it in its simplest form. So an integer would be simpler than a character, which would be simpler than a string. So you want to pick the easiest one there. Now that we've seen a couple different ways to declare things at the beginning of our code, we'll take a look at a different function that we can use and one of the commands that we can use when we program. So this command, pin mode, would typically go in the setup section of your code. And what this pin mode command does is it configures a certain pin to behave as either an input or an output. So as an example, if you had something like a photo resistor connected to a pin, you would want that pin to behave as an input. You would want that pin to read the information that was being fed to it from the photo resistor. So you could see what's the status. Is it detecting light or is it not? On the flip side, if you had an LED connected to a pin, rather that's integrated into the board or an external LED, you would want that pin to behave as an output so that you could turn the LED on and off. So at the beginning of our program, we usually set up our pin modes for all the pins that we'll be using. And the syntax here is pretty simple. We just write out pin mode, all one word, and then we have parentheses. So in these parentheses here, we have the pin number that we are setting, and you can refer to the map. That's why I talked about the map so much, is that you'll need to refer to it to select your pin numbers. So you'll refer to the pin number that you're setting and then your mode. So mode can be a couple different things. It can be set as an input, an output, or an input pull-up. So we'll get into the pull-ups later, but most of the time you will be setting your pins as either an input or an output. Here's a short example stringing together everything that we have talked about so far. So you can see in the beginning we're declaring our variables. We only need an integer because we're using a number, or in other words, a pin. So we're referring to pin 14, and we're going to give this the label LED pin. So later on in our program, whenever we say LED pin, we are referring to pin 14. So here is our variable declared, step 1. Then you'll see that we have our setup command here. We have void setup, open close parentheses, and then we have our first open curly brace. And so in that we have our setup and we have our pin mode command. So we have our pin mode command, first parenthesis, we are going to refer to LED pin. So this is a little bit different. We're stepping up the complexity just a little bit, but in a way to make things simpler. So you could also write this as the number 14. Get my different color here. You could also write this as the number 14 to refer to pin 14, but we've done things correctly, and we've already declared this as a variable to begin with. So instead of writing pin 14, we can write LED pin as our label, and it's going to point back here and recognize that this is pin 14. And then we're going to put a comma. I don't know if I mentioned this before, but you'll need a comma to separate these. And then we're going to set this as an output. So we're going to put output after that, close the parentheses, and add a semicolon after. So I think this is something else I didn't mention last slide, but you will want to add a semicolon after this command as well. That's kind of a general rule to signal that the command is at its end. And then you can see I've also added a comment by using a double backslash. And this is just noting that we're setting a digital pin to be our output. And so again, the beauty of declaring things at the beginning is that if we needed to change this pin, I could just go up here to the beginning of the code and do that. I wouldn't have to hunt down to find out where it was in the setup or later on in the code. I could just do that in one place. So this is how we string together declaring our variables, specifically declaring an integer. We have our setup section of our code, and we're using pin mode to declare pin 14 as an output. The next command that we'll take a look at is the digital write command. So this is written, well, we'll see in a second when we look at the syntax. So the function of this command is to write a high or low value to any pin that's recognized as a digital pin. So if you'll remember, thinking back to our pin map, I mentioned digital read and digital write. And the meaning of those wasn't clear. We just knew that only some pins had that function. So now we're going to look at the function, and hopefully this will make more sense when you think back to the pin map. You'll see which pins are able to do this because not all of them are. And so also it's important to note when I'm talking about the function of this, writing a high or low value to a pin, that essentially means a 1 or a 0, right? We're turning the pin on or off. So usually this is when a pin is declared as an output. We can turn it on or off, aka declare it high or low, using the digital write command. So an easy example of this is turning an LED on or off. We could use digital write to assign that pin a value of high or low, and that would turn the LED on or off respectively. So how we write this command, the syntax of this is we put our command digital write here, and then our first parenthesis, and then the pin number or the label for our pin. Either one can go there. Then we have a comma, and then we have the value. So that's going to be high or low, just simply the word high or low. We're going to close that with another parenthesis, and then as always end with a semicolon. So we'll take a look now at what that looks like in practice. Here's our snippet of code from before. Everything on the first 4 lines is the same. We are just adding on to it. So you can see we've declared our variable. We have our setup loop. We've closed it with a curly bracket. And now we're declaring our loop. So the main part of our program. So just to refresh, we're calling pin 14 LED pin. We've made this pin to be an output, and so now we're going to turn this pin or this LED on because we're assuming that there's an LED connected to this pin. So the way we do that is we have our digital write command. Then we're going to put LED pin. Remember, you can put a specific pin number or you can use a label. And then we're going to set this to high. So high equals on, low equals off. So by setting this to high, this would turn anything that's attached to that pin on. Likewise, if we had the next line to say digital write LED pin, and we had this to say low, that would then go in and turn that pin or turn that LED off. And so here you can see we are building with our label. So we have LED pin is referenced in 2 places in our code now. So if we needed to switch pins and change this to pin 12, instead of having to do that in 2 different places, and try to make sure that we have everything and read through our code, all we would have to do is change this at the top. And then so everywhere that we're referencing LED pin, it would just circle back to the beginning, and it would say, okay, I know the LED pin equals pin 12. So again, I'm just reiterating that it's always good to declare your variables. It will make your life easier. If you have to change something, you're less likely to make mistakes, and it's a good coding practice. So I just want to keep harping on that so you can see why it's so important and why it is so practical. Here's an example of the digital write command being used in an actual program. And so we have our void setup at the beginning, very important, close parentheses, open bracket, a curly bracket. We have our comment that we're setting apart by a double dash, and then, or a double slash rather, and then we are using our command pin mode to set the mode of the pin. Now you'll notice here or I've just highlighted, I'm not using a pin number. I'm actually using LED underscore built in. So something that's unique about the Arduino Uno is that it has a built-in LED that's connected to pin 13. And so what that means is instead of connecting an external LED or something to this pin, I can use the integrated LED and use that in my program to test it. So I really could write pin 13 and it would do the exact same thing. But in this case, you can also specify LED underscore built-in and it will reference that pin. So these two are interchangeable. If you're using the built-in pin, you might want to remind yourself of that by using the term LED underscore built-in. If you are connecting something external to that pin, then you may just want to use the pin number 13 to help kind of keep those separate in your mind. Okay, moving on, then I am declaring that as an output. And then moving down to the void loop, I am using my digital write command. Make sure you capitalize the W. I'm going to use my LED underscore built-in nomenclature, again, interchangeable for 13 because it's connected to pin 13. And then high. So this high command is just going to turn the LED on. If I had this set to low, it would turn the LED off. And that's how we can use digital write in a program. Next command that we're going to talk about is the delay command. So before in assembly, if we wanted a delay or a timer, we had to set a register to a value and decrement it in a loop, right? So delays are a little bit easier to program in C language, thankfully. And the reason why you would want a delay is to pause the program for a specific amount of time before you continue onward. If you have LEDs blinking, if you don't add a delay, it's probably going to be really hard to see that because it's almost instantaneous that your program would be turning them on and off. So you'd want to incorporate a delay so that you can see what's happening. Or to pause if you needed to wait for something to change or anything like that. So when we're talking about delays, we don't refer to them in seconds. We actually have to convert our delay time to milliseconds. So I've added a note here, 1,000 milliseconds equals 1 second. So try to remember that when you're coding. If you need to delay something for 5 seconds, you're going to have to program it as 5,000 representing milliseconds. So the way we write in a program delay, this command here, again, very simple, very intuitive. We just have the word delay. And then, as usual, we have some parentheses here. And in those parentheses, we're going to write the number of milliseconds that we want to delay our program. So before I used the example 5,000. So we could write that in our parentheses, which would be 5 seconds. So it can be as long as you want. Just make sure that you're converting that time to milliseconds. So that should just be a number in these parentheses. And then as always, we're going to end this command with a semicolon. Now, just like before, I'm going to circle back to the same example. We're just going to add our new command in here to make it a little bit more complex. So a quick refresher, we're declaring our pin, assigning it a label. We're setting our pin to be an output, starting our loop. Let me switch to the different color. I think it'll be easier to see here maybe. So we're starting to our loop. Then we are going to digital write the pin to high. We're going to turn it on. And then we're going to introduce our new command, our delay. So we have the delay command, the time written in milliseconds. So remember, 1,000 milliseconds equals a second. So if you ever need to go the other way and know how many seconds the delay is, divide by 1,000, and that will tell you how many seconds. So we can see that this is a delay of 1 second. The LED or the pin is going to be high or on for a second, and then it's going to move on to the next line, which is our digital write command again, and this time we are setting the pin to low. We are turning it off. So this is setting pin 14 to high, it's waiting 1 second, and then it is setting the pin back to low. So what this program is going to do, if this pin number is connected to an LED, is it's going to turn that LED on for a second, and then it's going to turn it on, it's going to wait 1 second, and it's going to go to the next line of the code, and it's going to turn that LED off. So you can see here, this is how we are combining declaring our variables, setting up our inputs and outputs. We're setting things high and low, and we're integrating some delays in there to make it visible. If we didn't have this delay, chances are you would not be able to see the LED turn on and off because the microcontroller would be executing the code too fast for the naked eye to see that. We are now on to our last command for this lecture, and that's going to be the serial print command. So what this does is it will print any data that you have declared or any data that you note to the serial port as human readable text. So you'll have what's called a serial port where you can kind of see the outputs of a program happening. And so this is where it will print your text. So in this context, bytes are a single character. Anything that has 2 decimal places we refer to as a float. And characters and strings are characters and strings as we've previously defined them. That's anything with a single character, or a string is a group of characters or a group of words. So the way that we write our serial print command is the word serial, and then we have a little dot in here. So you'll remember digital write was kind of all smushed together. Pin mode is 2 words kind of smushed together. This one, they're separated by a little period in the middle. So we have serial. Make sure that you are spelling it S-E-R-I-A-L. Cereal, not C-E-R-E-A-L, as in a bowl of cereal. There's a difference. So we have serial.print, and then as usual we have our 2 parentheses ending in a semicolon, and in these parentheses you can put any text or any number that you want printed. So ideally this text is just a label that's referring to text that's declared early on in the program. But if you only need to print something once, you might not want to declare it as a variable. You might just want to put it down here in the parentheses as is without assigning it a label or anything. So we'll take a look at some examples, some things that we can output using serial print. So in this first example of serial print, we have 78 within the parentheses. This will print out the number 78 for you to read. Next, in the parentheses, we have a number, but it's a longer number, 1.23456. And it's important to note that if you don't specify otherwise, when we're serial printing, it will typically only reference 2 decimal places. So if we really need to, we can change that. Typically, this is all that's needed. This is all we'll need for this course. But just note if you need more than 2, that'll take some extra work there because serial print typically only prints out 2 decimal places. If we want to print out a character or a string, we will need to put those in parentheses, or I'm sorry, in quotation marks. So here we have an N, and if we put this in quotations, it's going to print the letter N for us. So numbers we don't have to put in quotations. Characters or strings, they do need to go in quotation marks. Last example, instead of just a single character, we have a string. So if we say hello world and then a period, we need to put these in quotation marks. It will print out hello world and a period. So something that's important to note is that it will not print out these quotations here. These quotations are just necessary. You need to use the quotations as part of your serial code. But here on the right side, I'm just using them to indicate what's being printed. So you would not see these in the actual printing, but you do need to build them into your code. Something else we can do to take the serial printing command a step further that's kind of interesting is that we can use it to specify our number system base as long as the base that we're using is binary. It could be octal, which is base 8, decimal, or hexadecimal. And so what we see here is in our first couple examples, here we're asking it to print serial print 78 as usual, but then if you add a comment a comma, and one of these abbreviated base systems, so BIN stands for binary, that's going to print out the number 78 in binary form. So instead of doing that conversion or trying to calculate that conversion, the serial print command can do that for you. So this would be really great if you were building a microcontroller that acted as a converter. So it would take in a number in a given number system, and then you could use serial print to give you the output in a different number system. Much like a calculator can actually do on your computer. So another example, same thing, except if we use OCT for the octal system, this will give us 78 represented with the octal number system. That's base 8. We haven't really covered that, but it is an option that you can use with serial print. Of course, we could do comma DEC for decimal, but that's just going to give us 78. So if you're already working in the decimal system, that doesn't really gain you anything. You don't really need to add that. If we added a comma and hex for hexadecimal, that would print out 4E, which is representing 78 in the hexadecimal number system. So we can use serial print to kind of convert numbers to different number systems. Something else that we can use it to do is to determine the number of decimal places. So I mentioned to extend your decimal places beyond the typical 2. That takes an extra step, and we can see that here. So now if I add a comma and a 0, that's going to give me 0 decimal places when I print, which will just be a 1. In the next line, if I just do a comma 2, it's going to give me 2 decimal places when I print. That's standard. Next line, if I specify comma 4 decimal places, it will print out the number to 4 decimal places. And when you're using the decimal place command to differentiate, after serial print, we do need to add the letters LN. So these first 4 examples up here, try to group those together. These first 4, we do serial print as normal, and then a comma and the base that you want to use. And then to change the number of decimals that are displayed, we use serial print LN, and then a comma and the number of decimals that we want to see. So we can use serial print in a myriad of different ways. We can use it to print things as is. We can print integers in different base systems, and we can use it to control how many decimal places that we see. So this first component is probably familiar to most of you. This is just a simple LED. The important thing to note here is the positive and negative side. So the positive side is usually, or is always, the longer wire, and the negative side will be the shorter wire. You can also note most LEDs, they will have a flat side or a flat edge up here. Or if you look on the red one, it'll be in this area, same spot. And the flat edge indicates the cathode. So that being said, when you look over here, what does that mean, right? Anode and cathode. When you look in the second diagram that I have here with the red LED, you'll see that the anode can refer to the positive side and the cathode refers to the negative side. So it's important to properly orient your LED when you're building your circuit. And generally you'll get a schematic that will either look like this one over here, or in typical circuit representation form, it will look like this one all the way over on the right. And so you'll notice that it has, this one has the anode and cathode labeled. Typically they're not labeled. You would just see this symbol right here in the middle of the triangle with the 2 arrows coming off of it and the line. This is the circuit representation for an LED. And so what's going to be important to remember when you're looking at a schematic is that an easy way to remember what the negative side is think this little negative bar corresponds to this bar running up and down in the diagram. So whichever side this bar is on, that's what side the short leg, the flat side, or the cathode side of your LED should be oriented in your circuit. Our next component is simply some jumper wires. So if you bought the kit or if you're working off the components in the lab, you will have wires that look like this. They'll come in all different lengths, and usually they will be color-coded by length, and all we're doing is using these wires to make connections. So you'll notice that there is an exposed wire at each end of these, and this is just what we're plugging into our boards to make those connections. So what are we plugging the wires into besides our board, our microcontroller? Well, you're going to be using a breadboard to start connecting additional components to your microcontroller. So this is a small breadboard right here. You'll notice there are positive and negative rails running along it, and then there's a space in the middle where we can arrange different components. And later on, I'll cover kind of the setup of a breadboard and how to properly use one. But I want to finish reviewing the components and how you would typically see a circuit set up, because I think it's a little bit easier to understand how a breadboard works once you have a little bit more concept and context of setting up a circuit. So we'll look at those, we'll come back to these. Something else that's going to be really important when you're building your circuits is properly integrating resistors. And so resistors typically look like what you see in these photos here. The top right one, a resistor is plugged into a breadboard, which is what we just talked about. So we use resistors to limit our flow of current so that we're not burning components up. So these are very important. It's also important to make sure that you're using the correct resistors. So in most of your labs, I take the guesswork out of it for you partially by specifying which value of resistor to use. So you'll see resistors with values that we call ohms. That's how we measure the resistance. You might see a resistor that's 1 ohm, 100 ohms, 1000 ohms, 1500 ohms, anything like that. And so it can be difficult to tell these resistors apart, but you might notice that there's different colored bands. Every different value of resistor has a different combination of these bands. So I've included a resistor chart for you to help identify the proper resistors. And so you can see, depending on if you're using a 4 or 5 band code, some bands are indicating the value, and generally the last band indicates the multiplier. And you'll also notice that these bands are oriented more towards one side of the resistor than the other. Let me grab a color that'll show up well. So in this graphic in the bottom right side, you'll notice this gold band is a little bit more towards the middle, and this brown band is all the way on the edge. We see this as a 4-band resistor. And so this is probably flipped backwards compared to our 4-band code that we have at the top. We can see the gold resistor would typically be the one all the way on the right. And we see that's because it's kind of far off on its own, and the other two are oriented more towards the brown band. So we know that the gold is our multiplier. Also, a clue is that gold and silver only act as multipliers. They don't clue you into the value. So what you would do, we can read the value of this circuit. So we have a 4-band circuit. Let me get rid of some of this here. So we have a brown band all the way to what would be the left. We're kind of flipping it around here, so that would be a 1. And then we have what looks like a gray band, which would be an 8. Let me flip it the correct way down here. So we have a 1 and an 8. And then we have an orange band, which is going to be our multiplier. We notice in the 4-band code, if we follow the line, we see that this third band ends up being our multiplier, and that is going to be 1K. And so what that means is this resistor is 1800 or 1800 ohms, and then this gold band all the way on the end tells us the tolerance, and that just means it's going to be within plus or minus 5% of that value. So you don't have to worry about the tolerance too much. It will just be important to make sure that you're getting the right value of resistors. And I will try to remember to add in the proper color code for these components in the different labs. Typically in class, you only have the correct resistors available to you. I usually pull the bins out from the lab and bring them to class. So that takes some of the guesswork out. But if you go to the Tusk campus in the engineering lab, the electrical lab, they do have all the little bins labeled with the resistor values. If you've purchased the kit and you're working at home, as I said, I will try to include the colors for you, but you can always refer back to this chart and figure out which what the band color is that corresponds to the value. And when in doubt too, you can also Google it. I have no doubt that if we Googled the resistor band code for an 1800 ohm resistor, you would find this picture here that we just walked through. So you certainly have a lot of resources available to tell the difference between the resistors. Just make sure that you're using them, because if you use a resistor that is too low, you could burn out some components, and if you use one that is too high, the current will not be able to flow properly and your circuit will still not work. Here's a simple circuit diagram that's shown two ways. So the method on the right is a wire diagram or wire schematic. This is what's used in technical settings and what you'll commonly encounter. The graphic on the left is just a more physically accurate representation of your board setup. It is not used generally in technical settings. It's just used, I think, for beginners. It's really good to give you a better understanding of where things are plugging in and how your setup should look. So you'll notice in your lab that I have included both of these documentation types to help guide you in setting up your circuit. So when you see these two different ways in your lab, it's not two different circuits or two different ways to set things up. It's the same thing, just represented two different ways. So now we'll go ahead and look at how to connect an LED to your circuit. So the first thing you want to do when you are connecting things to your circuit is to ground them. And so in this case with an LED, we're going to ground the negative side. That's the cathode side. So if you have anything with an anode and a cathode, you usually want to make sure that you are grounding the negative side of that. And then that puts our anode side over here. An easy way to remember that is that the negative side is the straight wire on the LED, which is the same as the negative sign, right? And so that's what I use to help me remember which is which on an LED, because I know sometimes it can be confusing. So we'll want to connect the cathode to our ground. And then to the positive side of our LED, we'll want to connect a resistor. And then that resistor will just be connected to a pin. So we can connect this to any pin, barring limitations on the pin, right? I talked about how only certain pins are analog pins and so on. So within reason or within certain limits, you can connect to any pin or a variety of pins. So this one we're connecting to pin 3, and so in our program when we note pin 3, that's what's going to control this LED. We could just as easily plug this resistor down here into pin 8, and we could control this with pin 8. And so any of these is acceptable. You can kind of connect it anywhere. The only thing I don't like about this format here is that it does not show how the breadboard comes into play. So if you imagine you would have a breadboard with a little hole here that you would plug in your wire to, maybe another on the same path that you plug in your LED. One here to plug in your resistor and another here to plug in your LED. So it doesn't show that, and we'll talk about the breadboards more in depth shortly. but just bear that in mind that a breadboard does come into play with these. Okay, and then it's the exact same thing represented over here on the wire diagram. It just looks a little bit different. And now I'm seeing. So this is connected to pin 13. I told you this was pin 3 over here on the left. That was my mistake. It's actually pin 13. The way this is written is just a little odd. So this is actually pin 13. So same thing, pin 13, you see we have a resistor here. This is the symbol for resistor in a wire schematic, and it's labeled as 220 ohms. So this is the positive side, or the perk of having an actual wire diagram, is that all of your components are clearly labeled. So you know exactly which resistor to use, and you know what the components are. So here we have our resistor connected to our pin. It's going into our LED. And you can see in our schematic, it even helps us note which is anode and which is the cathode side. So here, the cathode is the negative side, right? And we know we connect the negative side to the ground. And you can see there's this little bar across the bottom of the symbol. So again, that's just another easy way to remember that's where the negative side of your LED should be connected. Moving on, we see our LED is connected to ground, right? We're grounding it. This is a little bit different because instead of showing ground in its actual position on the board, we're just representing it at the bottom. We don't really need to represent it in multiple positions to understand that things need to be ground. We know we have 3 pin options to ground things. We can use any of those. So this schematic here is just showing us that this should be grounded. And so that's the schematics for doing a basic circuit with an LED, both in a technical wire diagram form and a less formal pictorial form. So a few slides ago, I introduced breadboards, and now we'll go ahead and take a look at how we work with them, because you have to plug your components in a certain way for them to work and for them to be connected correctly. So down the sides of the breadboard, you see we have the blue and red lines, and these are our vertical bus strips. They are continuous down the entire board. And so there is a positive rail and a negative rail. And so our negative, remember, is for ground, or if you're not familiar with it, we ground to the negative side. So if you'll remember on our circuit before, we had a wire coming from the ground pin and connecting to the LED. What we would do is actually take a wire from the pin over here, and you always want to ground to this rail first. And so what that means, all of these are connected. You can see by this green line running down. Each of these little squares is a hole on the board, if you haven't made that connection already. And so looking down this negative side rail, all of these little holes are connected. So that means if I ground to one place, anything else here that feeds in will also be connected to the ground. Anything else on this green line. And same for the red, but we really don't need to use that right now. It will just be important that you are grounding to the ground rail. And so you'll also see, looking over in the diagram on the right side, that over here, our horizontal holes are linked together on the board. And so what that means, you can even see, I don't really need to redraw all over them, but the yellow lines are representing all of these holes are connected. So when we're drawing our components in, what you don't want to do is stick a leg of a resistor in here and then stick the other leg in here. It won't do anything, or it won't go anywhere. It will just be connected on the same section. So when you're connecting components, if this was our little resistor, this would not be a good connection. What we would want to do to properly connect it is to span between linkages. So I would put one leg here, and then I would probably come down to see wherever it fit comfortably, and I would plug the other leg in here. So my resistor would be spanning 2 different kind of linked lines. And so that's what you want in a component. The same component generally does not occupy the same line unless it's a push button. Sometimes it does. But so my resistor would be here. And then if I needed to connect it to an LED, get rid of this one, my LED, one leg would need to be in the same row to be properly connected. So it can be any of these. It doesn't matter because they're all connected, remember. Oops, I keep trying to grab my eraser here. And so you could put the leg of your LED in this hole, for instance, one here, and then you could put the second leg up here in the next row, and then you would have a wire connecting this to the ground. And so because your LED and your resistor would be in the same row here, they would be connected. That would complete the circuit. This is a little bit hard to explain, but I think the next slide, when we look at an actual circuit, will help us out. One other note is that the rows are not connected across the divider, as you'll see. And so if you have a component that spans the divider, for instance, plugged in here, that's perfectly fine. That counts as being plugged in two different spots because this entire row is not connected. So let's look at the next slide and hopefully we can make this make a little bit more sense. So now that we've learned more about breadboards, we can take a look at what it actually looks like when we introduce one to our circuit, or what that looks like in person. So I brought in just our pictorial representation on the bottom right of how we would connect just one LED into our board in a real simple way, and this is what it looks like in practice on this larger picture on the left here. So you'll see I'm using this black wire here. It's running to the ground pin, and typically we use black wires to represent grounding. Red would represent any power, and then I try to use different colors for different things that are connected. So if you have different color LEDs, you may want to use different colors, and so on. But that's really up to you. I think the most important thing is just it's good practice to use those black wires for grounding and red if you're adding any additional power to the board. Otherwise, the power is going through the board from the pins, so you typically don't need to connect that. Okay, so we have our black wire connecting us from ground, just like here in our schematic, and that's going into our LED. Now, you'll see this whole track here, this whole column is all grounded. These are all connected in this direction that I have just ran across here with my purple highlighter. So we can stick this LED into any of these pins on the breadboard and have it grounded. So we've just chosen this one. And now we want to put the other leg in a brand new row to keep those connections separate. So we've just put it in row 5. Now we need to connect a resistor to our LED. And so we want to make sure that the resistor is connected in the same row, right? This is now making a connection. And we could put our resistor over here. Doesn't really matter as long as it's in the same row. Now what we don't want to do is connect the other end of the resistor up in this same row. Then it's not really going anywhere or doing anything. It needs to be in a separate row to make a separate connection with something else, which we want. We want to connect it to this green wire. So it's connected at one end to the LED. We put it in another row, row 10, and then we connect it with this green wire back to pin 13. And so you see we're completing that connection. And so this is pretty simple. This LED again, or this resistor, could be in a different row. We could connect this to the wire in row 9, row 8, doesn't really matter. As long as you're keeping your rows separated appropriately with your components, and you're grounding things and connecting to the right pins. That's really the most important things when you're setting up your circuit. But this is the basic connection for setting up an LED. If you really wanted to make things look a little nicer, something else you could do, instead of connecting your LED directly into the ground line here, what you could do instead is we could put this leg of the LED up here in row 3. And then we could put a wire running from this sort of ground line over to row 3, and it would be connected. And it just helps the LED, you're not kind of pulling the wires apart so much, and it can look a little bit neater if you have several components to connect. So really, as long as you're making the appropriate connections and you're following the rules of a breadboard, you should be fine. Here's how we would connect multiple LEDs, and I want to review this specifically because it is part of your lab. This really applies to any component, but LEDs are a nice simple component for us to use. It's essentially the same principle as connecting one LED, just duplicated. But there's some nuances that I want to cover to make sure you're not running a bunch of extra wires to hopefully help you out. So you'll see we have our black wire running from ground to our ground line on the breadboard, right? So now everything in this column will be grounded. And so you'll notice, as I mentioned previously, the LEDs don't have to plug directly into this ground line. We can connect them with wires. And that's exactly what we've done. So this wire now is going from that ground to connect to this row. And so here's where it's connecting to the LED. So we're not plugging the LEDs right into this ground line. We are connecting them each on their own row. And it just keeps things a little bit neater, especially when you have multiple components. Okay, so we've connected the LED now to the ground on the cathode side. Remember, that's the negative side or the straight side of the LED. And on the anode side of the LED, we're just going to put it in the row right below the one it's currently in. And this is easiest when you get the LEDs, the anode and cathode are typically close together. So it just makes it easier to plug them into rows that are right above each other because we can do that, right? The connections are separated by row. And so that's perfectly fine to do, again, as long as each connection's on its own row. So this first connection is made to the ground in its own row, and then in the next row we're connecting to a resistor. Now you might notice, let me get rid of this highlighting, you might notice this resistor is spanning a gap and then it's connecting to a wire in the same row as the LED. So typically connecting multiple things in the same row is a no-no, right? We don't want to do that. However, these rows, as we just saw, are separated by this gap here. So the rows on the left side are not connected to the rows on the right side. And so that's why this resistor can span this gap and stay in the same row. It helps keep things nice and neat, and everything is still separated like it should be. So just something to keep in mind, again, the rules of the breadboard. So on this side, it's connected to the LED. On the other side, it's connected to a blue wire that leads into a pin. And so this is just duplicated for every single LED. And again, this is where it's nice to run a wire from the ground line to the LED, keep things nice and neat. The LED carries over into the resistor, resistor into a wire, and the wire into a pin. So if you're setting up multiple LEDs, really multiple components of any sort, this is sort of a best practice way to do them. You don't have to set it up this way, but again, as long as you're setting it up and following the proper rules of a breadboard, really anything works. Let's go ahead and we will review Lab 4.0. So the objective of this lab is to use C language. This will be your first time programming in C, and you will be programming both an integrated LED and you will be connecting some external LEDs. So for part 1, you're going to blink an integrated LED, and I've given you most of the code that you need here, but I have asked you to fill in the missing pieces. So you'll need to fill in the pin number, you'll need to fill in this digital write information in both cases to turn the LED on and off, and put in an appropriate delay. And so I outlined that here. To turn on the integrated LED, again, you can use either pin 13, you can fill that in, or you can use LED underscore built in. right? They're essentially the same thing for that integrated LED. And I do specify a time. So turn that on for 1 second and then turn that off for 1 second continuously. Next, I ask that you connect an external LED to pin 13. So I've asked you to connect it to pin 13 because this is what your program is already set up for. So you don't need to make any program changes. And if you connect it properly, what you should see is your integrated LED and your external LED both blinking. So this is a great way if your external LED is not blinking, you can troubleshoot and you know that it is something in your construction that is incorrect because you should have verified your code in the previous step. So again, by using pin 13, we can verify our construction. And if you follow either of these schematics, the pictorial or the wire diagram, you should be just fine. If you feel like you need a little bit more instruction, you can just refer back a few slides to where I go into a more detailed explanation on how to connect an LED to an Arduino board. But it's pretty simple, pretty straightforward. Part C of part 1 is changing the program. So now blink the LED for 5 seconds on and then 5 seconds off. So before it was blinking for 1 second on, 1 second off, change that to 5, and you don't have to recopy your code here. I just ask you to tell me, what did you change? What line did you change? Or what lines did you change to change the blinking and the delays for on and off? For part 2, you're just going to blink LEDs in an alternating order. So you're going to add a second external LED to your circuit, and you'll add a couple more lines to your program so that you alternate between blinking two LEDs. So you should light up your first LED for 2 seconds, and then light up your second LED for 4 seconds with 1 second in between blinks. So your first LED would light up for 2 seconds, and then it would turn off, wait a second, and then your second LED would turn on for 4 seconds, and then it would turn off for 1 second, and then the whole thing, of course, will repeat. So here, the main goal is to get that second LED connected and modify your program to accommodate that according to the blinking structure that I've outlined here.